What's up, Recalculus? Let's go through a few examples of how to solve polynomial and rational inequalities graphically. And once we get the graphical situation all handled, we will transition to solving these algebraically using something called a sign analysis. All right. But yeah, anytime we transition from an equation to an inequality, just realize it's always extra. Always extra. All right, let's take the first function here, and why don't we just find the zeros and sketch the graph. All right, so we're going to set the function equal to 0. And we will diligently try to solve this, perhaps by factoring. And it's working out pretty nice. The function does factor x minus 5, x plus 3, and that's going to allow me to solve, setting each factor equal to 0. I guess I kind of jumped the gun on that last one there. And yeah, here are the 3 zeros of the function, the 3 solutions to that equation. And when we go to graph this function, these will be the 3 x-intercepts on the graph. But yeah, like I was saying, if you're solving an equation, we'd be done. We are transitioning to inequalities, and yeah, this is extra. So let's think about what the graph would look like. I hone in on my leading term of x cubed. The degree is odd. The leading coefficient is positive. And I know the ends of my graph will point in that direction. So let's play our old game of connect the dots. All right, I know I've got to start low, connect the dots, and high. Each of these zeros are multiplicity 1 because each factor appears only one time in the equation. So at each of these values, I will cross through the x-axis. It might look a little like that, okay? Well, for the first part of part B down here, state the solution equals, we already did that. There we go. Just repeat the answers from above. For the next couple questions though, now we have to not worry about where it's equal 0, but where it's less than or greater than 0. So just kind of notice something here. Every y value along that section of the graph and that section of the graph has an overall negative value. I'm just going to denote that there. All the y values are less than 0. And as I examine the other portions of the graph, all of these y values and all of these y values, they are all positive. And maybe it could be worth a moment or two to summarize this on a little number line down below, and this will be kind of what we transition to doing eventually without the graph when we do the sign analysis completely algebraically. But I'll notice here at -3, the y value itself is not negative or positive, so I'm going to put an open circle. At 0, same idea. The y value is not negative or positive, so I'll put an open circle. And when x equals 5, again, that y value is 0. Doesn't count as either negative or positive. But just to record the signs down below, everything in this region of the graph, negative, has an overall negative y value. And everything from these regions here has a positive y value. I might as well show the infinities on the graph as well. So if I wanted to show the solution to this inequality, I'm basically looking for where this function's graph has a negative y value. Well, that occurs this region here and this region here. If I just read that off from left to right in some beautiful interval notation, I get those two intervals. And if I try the same thing to try to answer the inequality, where is this collection of terms greater than 0, meaning positive, it's going to be the same answer as looking at the graph of this function and reading off where those y values are positive, which I'll highlight in blue there. And now I can write my solution set going from -3 to 0, left to right, low to high. Notice I'm using parentheses because at -3 exactly, the y value is exactly 0, as I've mentioned, and that does not satisfy that inequality. And the other region lives over there. So we have used the graph to determine each solution equal 0, less than 0, greater than 0. So I'd like to try a couple more with you here and maybe go a little bit more quickly through each. Let's examine number 2. What I love about number 2 is it's already factored for us. So that is a great start. We've just got to find the zeros, maybe note their multiplicity, and sketch the graph. Okay, setting each of the factors equal to 0 gives me these 3 solutions. And yes, multiplicity 1, multiplicity 1, multiplicity 2, bounce, cross, and cross. Let's think of the leading term next. All right, so we've got that negative sign. We've got an x, and an x squared, which will give me an overall leading term of -x to the 4th. Okay, think of the even power, think of the negative leading coefficient, and we know the two ends of our graph will both point down. All right, let's play the connect the dots game, everybody. We've got x equals -1, x equals +1, and x equals 3. The ends both point down, and at -1 and +1 we cross, and at +3 we bounce. Let's make it happen. Okay, something along those lines. All right, let's think about now the solutions to each of the following. We've got the first one already figured out. I didn't necessarily ask for multiplicity, so I didn't include it there. But now let's think about the next two. Notice we have less than or equal to 0. Greater than or equal to 0. That extra equal sign does mean now that the endpoints here are very much in play. So let's analyze the graph, and I'm just going to pause the video here and highlight the positive and negative y values. Okay, welcome back. We now can see as we show the negative y values in pink and the positive y values in blue. I've summarized that down below here on a number line. Again, this will be something you see again in the sign analysis. In fact, this is a sign analysis of the y values. I'm actually going to go answer the last question first. It is a little less cumbersome. We're going to analyze the sign of the y values of the graph to determine where it is greater than or equal to 0. That would only be this portion here. And on the number line, I've shown that as the x values that live between -1 and +1, including the endpoints. And that is why I'm showing brackets. This one's a little more interesting because, well, there's more than one section. In fact, two of them, because of the bounce, are back to back. So here's what I'm going to do. First of all, I've pointed out on the number line, because of the equal sign, I'm showing the endpoints now in a closed circle. And if I just go and darken the intervals of interest where the y values are less than 0 or negative, I see this first section is going to clearly be included in my solution set. So is the third section between 1 and 3, including the endpoint of 3. And then so is the section between, well, from 3 to infinity and beyond. And since the 3 is included in all of this, when you kind of take these two back-to-back sections, there's no breaks, there's no interruption. It actually just ends up being one gigantic section because the 3 is filled in due to the equal sign. So I can just report this very cleanly now as two intervals, one from -infinity to -1, bracket, and the other one interval goes from 1 to infinity. Now you may be wondering, well, lady, what if there was no equal sign there? Well, if there was no equal sign there, there'd be an open circle here, and that would actually include a break in the two sections, and you would report that as two separate intervals. Crazy, right? Gotta pay attention to those details, everybody. Well, that's enough for this video. I hope you learned a little something about the starting off of a sign analysis. Don't abbreviate analysis.